Hi, I'm Giuseppe, and I'll present our new paper introducing MatFuse, Controllable Material Generation with Diffusion Models. Throughout the presentation, you will find the QR code linking to the project page in the top right corner. Materials play a central role in 3D graphics, describing light interaction with surfaces, which is crucial for realism in games, simulations, movies, and more. However, synthesizing materials is challenging. Procedural methods need expertise and time, while capture techniques rely on costly hardware. Deep learning offers an alternative solution, but most approaches lack the fine-grained control and art direction of traditional approaches, limiting its use in real-world scenarios. Several approaches have been proposed to generate materials using learning-based methods, with the most relevant being Material GAN from Go et al., TileGen from Zhou et al., and controlling material appearance by examples from Hu et al. However, these methods differ from MatFuse in the underlying generative backbone, as they rely on GANs. Additionally, they generally provide users a limited degree of control, being conditioned on reference pictures and input patterns. In contrast, MatFuse leverages a diffusion model-based architecture and incorporates multimodal conditioning to provide fine-grained control to the user. MatFuse is a conditional generative model that produces high-quality pixel-level reflectance properties while combining multiple conditions. We achieve this by breaking down a material into primitives like color palette and sketch, which guide the generation. It is inspired by the latent diffusion model and has two main parts: a compression network and a diffusion model. The compression network projects data from the pixel space to the latent space and back. The diffusion model learns the distribution of the latent feature vectors, enabling the generation of new samples. Moving on to the compression model of MatFuse, we introduce a multi-encoder VQVAE. This model compresses the input materials into a disentangled latent space using multiple encoders. This latent is then quantized before being passed to the decoder, which reconstructs the data in the pixel space. The use of a multi-encoder architecture allows the model to learn a disentangled latent representation of each material map. We can then manipulate specific parts of the material directly in the latent space, knowing which material property each channel encodes. By masking portions or channels corresponding to a specific map, we can force the model to generate only that particular property while keeping the rest of the material unaltered. In combination with traditional in-painting, it is possible to generate only specific areas of the material for all maps or for a reduced set only. We evaluate the generative capabilities of MatFuse in different conditioning setups. First, we show the results when guiding the generation with a single condition. We can see that for each input, the model is able to capture the most representative features and generate a new, realistic material that incorporates them. The animated renderings better showcase the quality of the generated materials and their realistic appearance. MatFuse is able to combine multiple conditions to guide the generation. In particular, we focus on the combination of a global condition, like the color palette or text, and a local condition, in our case the sketch, constraining the structure. We can see that MatFuse is able to translate the visual properties of the global condition to the material pattern provided via the sketch. We demonstrate the use of our volumetric in-painting approach for material editing. On the left side of the figure, we show the original materials, with the masked areas highlighted in green, and the maps that were entirely removed marked with a dash. Results show the method's ability to be coherent with the provided input, while filling the masked area, even in challenging settings where a single map is kept. Finally, we compare MatFuse with TileGen. Notably, MatFuse is able to generate materials with a comparable quality to TileGen, although the latter is limited to a class-specific training. These results are further confirmed by the user study, where MatFuse obtained a 43% preference compared to the 38% for TileGen. In conclusion, we presented MatFuse, a learning approach for the generation of materials. The proposed approach specifically leverages the generative capabilities of recent diffusion methods to produce high-quality SVPR maps, supporting extensive multimodal conditioning. MatFuse leverages the disentangled latent space to perform map-level material editing. We believe that MatFuse represents a promising solution to build upon for material generation tasks, Thank you for your attention. Visit the project page for more, including the link to the source code.